Okay, so as I was saying, we are at the end of the third week, lecture number 18, in terms of the quarter. In terms of a normal 10-week quarter, we are about 66, 67% done in terms of time, but material-wise, we have covered more than 75 to 80% of our material. Okay, and so we have plenty of time to actually answer student questions, go over some example problems, stuff like that. Let's look at logic gates. So how is all of this implemented, right? Now, even EE students, when they work with these kind of digital circuits, they work with building blocks. Okay, they work with building blocks, meaning you're taking a pre-designed or predefined element or circuit, if you will, and then you're going to use that to create your digital logic circuit. Okay, and non-EE majors especially, you're simply taking that element, and like an EE engineer would do, you would simply analyze a system based off of the building block. In this case, the building blocks for digital logic circuits are known as gates. G-A-T-E, gates. Okay, so I would say gates. The basic building block for digital logic circuits. Each one of these gates has a specific function, and they are comprised of, in terms of circuit elements, they are comprised of transistors. Yeah, they are comprised of transistors. The first and the most fundamental is the inverter gate, called the NOT gate, N-O-T, NOT. And in this case, the word NOT is standing for opposite, inverter. Okay, so the NOT gate is also referred to as the inverter gate. Gates are like building blocks, not like, they are building blocks. Input to that circuit is defined on the left, noted on the left. Output is noted on the right. On the left, this is the input. On the right is the output. Typically, an inverted input or output is noted by this dot, this circular dot. Okay, the dot notes inversion. So you can see there's an arrowhead similar to a diode. And the arrowhead has a circular dot, a small circle at the tip of the arrow. And that is the symbol for a NOT gate. NOT gate. The representation, as you can see here, is A and A bar. Say A bar, or typically we use NOT. So this is A. This is pronounced as A NOT. So if you see a bar over the letter, that bar is for NOT. Okay, so mathematical operation is inversion or opposite. In terms of a circuit signal, it'd be pretty much either out of phase, or in terms of digital logic, 5 volts would go to 0, 0 would go to 5, which is very basic operation of a transistor, very easy to implement. You can take 2 transistors and implement this very easily. Okay. The function of gates is displayed in a table that is known as the truth table. Truth table. Because it speaks the truth. If you give an input of 0 to A, the output is 1. If you give an input of 1, output is 0. As easy as that. Okay. Again, it's a mathematical operation. In circuit terms, it's simply the input of a transistor circuit, and the output of a transistor circuit is simply inverted. Okay, logic 0 and logic 1 are inverted. If you give 5 volts at the input, you will obtain 0 volts at the output. If you give 0 volts at the input, you will obtain 5 volts at the output. That's what it would mean in terms of circuit analysis. Okay, make sense? NOT gate is an inverter. A and A naught. Input A, output is A naught. Truth table only comprises of 2 inputs and 2 outputs. Obviously, you have one single input going in there, right? Okay, any questions? Okay. Then the second fundamental gate is the AND gate. AND. In this instance, the AND stands for multiplication. If you have 2 inputs, A and B, it is A and B, A multiplied by B. Like literally when you say A and B. Now in logical everyday life, our thinking is A and B simply means A plus B, right? And in everyday life would simply mean plus. But here in digital logic, the AND means multiplied. And this stands for multiplication. So you have 2 inputs. By the way, the inverter gate is the NOT gate is the only gate that has one single input. Okay, all other gates have multiple inputs. So you have 2 inputs, A and B, no pun intended. And the output is C. Output of C is AB. When you say AB, it stands for A multiplied with B. Okay. Mathematical operation is A multiplied by B. And so you can see 0 times 0 gives you an output of 0. 0 times 1 gives you an output of 0. 1 times 0 gives you an output of 0. The only output, the only state where the output is 1, meaning the output is high, is if both inputs are high. I'm sure there's a pot joke in there somewhere. Okay. So the output is high if both inputs are high. Hence an AND gate. In circuit terms, the output of that circuit would be 5 volts only if both inputs are 5 volts. I give up. Okay, let's just do it this way. 1 times 1 gives me 1. Okay, in circuit terms, if I'm thinking in terms of voltage, the output of this circuit would be 5 volts only when both inputs are also at 5 volts. And that is the AND gate. Okay, because it's multiplication. Now, here is the typical AND gate. So it's just 2 inputs. But in real life, you can have multiple input gates. Again, as I said, NOT gate, the inverter by itself, logically thinking, simply is the opposite. So there's no way you can have more than 1 input. But all other gates, you can have more than 2 inputs. Minimum, you need 2. In real life, you can have more than 2, 3, 4, 5, 6, 7, 8, as many as you want. That's a 3-input AND gate, A, B, and C. And so it's A, B, and C. Again, the output is high only when all inputs are high. Output is 5 volts only when all inputs to that gate are also 5 volts. If even a single input is at 0 volts, the output of that gate is at 0 volts. Okay. So the takeaway is, for an AND gate, the output will only be logic high or 1 when all inputs are also 1. Simply because it's multiplication. If you have even a single 0 anywhere, output goes 0 volts. So that's a 3-input AND gate. ABC simply means it's A multiplied by B multiplied by C. This is the result of the circuit themselves, right? Circuits don't know that they're multiplying. They don't know mathematical operation. It's just that the output of the circuit is such that the effect of the output is essentially a multiplication. Then you can have 4-input AND gate. It would be 4 digits or 4 bits, 0, 0, 0, 0. Result is still the same. The output will be high or 1 when all inputs are 1. And then the last, or the third gate, there are more gates, but these three are the most fundamental ones, okay? Is the OR gate. The OR gate is not, as the name suggests, OR in this case is addition. OR in this case is addition, or represents addition. So the answer or the output for a OR gate is C equals A plus B, the 2 inputs. Okay, symbol for an OR gate is this kind of, I always like to say it's like the compressed rocket symbol or something. There's a concave line, and then you have 2 inputs going in there, and then you have 1 output coming to the right. Oh, the NAND gate, I think, overlooked the symbol for a NAND gate. The straight flat line, and then a convex. Okay, convex output or semicircle output. And that's the OR gate, OR. OR in some ways is the exact opposite of an AND gate. The output of a OR gate will be 0 only when all inputs are 0. For all other combinations, the output will be high. Okay, so the output will be low all other combinations will be high. Right? You could have a 32-bit OR gate. All 31 of those 32 inputs could be at 0, but if even one input is at 1, then the output of that gate is also 1. Right? So in some ways, I always like to say the OR gate is the exact opposite of the AND gate. For an AND gate, it is always low. The only case where the output is 1 is when all inputs are 1. The OR gate, all outputs are 1, except for one combination when all inputs are 0. So it doesn't matter how many inputs you have. If you keep that in mind, you should instantly recognize an OR gate and an AND gate. Make sense? Let's take a pause before we move on. Again, these gates are going to be building blocks for digital logic circuits. Any questions at all? Next is the 3 input OR gate. Again, the same thing, only when all inputs are 0. Okay, truth table, and the expression remains the same, A plus B plus C. That does not change. Okay, that does not change. All right. Before we move on to the next slide, there are a few other things I'd cover about these 3 gates. So let's take a 10-second pause, actually longer pause if you need. Let me know if you have any questions. No questions? Okay. All right. So a couple of other functions. For a NOT gate, if you take the same number and multiply with its inverted output, the result is 0. So A times A naught, or A multiplied with A naught, is equal to 0. And this is kind of like a no-brainer, I think. A naught naught is A. This is pronounced as A naught naught. A naught naught is A. Okay. All right. Then for the AND gate, if we take the same and we give it to both inputs, so A and A, or A times A, gives us A. A times 1 is A. A times 0 is 0. A times B can also be written as BA, and ABC can be written as AB and C, which of course we can write as ABC. Right? If both inputs of an AND gate are the exact same, then the output is same. So it's 5 volts and 5 volts going in the input. The output of that gate is also 5 volts. Second one is similar. In this case, in the first case, we are simply saying A. A is a variable. It could be 0 and 1, right? So if A is 0, then 0 times 0 gives you 0. If A is 1, 1 times 1 gives you 1. If you have two separate inputs, one is A, the other one is 1, the answer would be the value of A itself. And A times 0 is obviously going to get 0. Make sense? Right. Then for the OR gate, where is my 3 input OR gate? Okay. So there's 2. Okay, there's 3. Oh, already covered this. 3 input OR gate. All right, then let's look at the other gates. How many of you have heard of the word NAND? Might have heard NAND flash. All our memory sticks, USB sticks, SSDs, say flash memory or flash drives. This is the fundamental building blocks of all storage that we use nowadays. Okay. All SSDs that you use, they use the NAND gate technology. It's one of the most easiest gates to implement. Okay, one of the easiest gates to implement. Oftentimes, you simply build the entire chip is made of NAND gates, and then you modify that NAND gate and create all other gates based off of those NAND gates. Because NAND gate can be implemented with just 2 transistors. Okay, so we studied NOT, AND, and OR, right? NOT, AND, and OR. If we combine the NOT and the AND gates, we get a NAND gate. Okay, so the N stands for NOT. Similarly, we have a NOR gate. A NOR gate, again, has an inverter in there. So when you combine a NOT and an AND gate, you get a NAND gate. And you combine a NOT and an OR gate, you get a NOR gate. So you simply take the output of the AND gate and connect it to the input of a NOT gate. That is the logic behind it. In real life, you have a circuit comprised of 2 transistors, and the output of that circuit effectively gives you a NAND gate. The output is AB naught. AB naught. To be more accurate, I would say A and B naught. And the truth table is the exact opposite of an AND gate. You have A, B, and you have the C output is AB naught. Zero, 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 1, 1, 0, 1, 1. Since it's the opposite, the output is 1 for all combinations except when all inputs must be 1. The output of a NAND gate goes to 0 only when all inputs are 1. It's the exact opposite of an AND gate. Okay. Then we have a NOR gate. The NOR gate is, of course, a summation. So the answer of the output is A plus B naught. A plus B naught. So again, A, B inputs, C is A plus B naught. table 0, 0, 0, 1, 1, 0, and 1, 1. This case, because it's A plus B naught, exact opposite of the OR gate, high output only when all inputs are 0. Only when all inputs are 0. Now, let's take a pause. Let me know if you have any questions. Any questions at all? So far, so good. Okay. There are some laws that were created by a person named De Morgan, known as De Morgan's laws. Okay, De Morgan's laws. The most common ones are here. If you are multiplying, meaning A times B, we can refer to it, or we can write it as, or implement it as a summation. It will be A naught plus B naught, and the output all naught. Okay, A naught plus B naught, naught. That's how you would say that. A times B, the AND function, the output of an AND gate, can be implemented by A naught plus B naught, the whole naught. Quite a mouthful. The reason is, sometimes, as I said, we'd have a building block inside a chip. We'd have multiple iterations of the exact same chip. If you have these kind of laws, then you can implement any kind of circuit using that same building block. You would not need a separate gate to implement everything. You would have one kind of gate, millions of gates on one single chip, and you can simply write a program. You program the chip to do the functions, which is an actual thing. There's a whole different branch of electrical engineering where you do chip designs. There's ASIC, and then there is custom. Sorry, not ASIC and custom. Custom is ASIC, which is basically the chips that we use in our smartphones, tablets, laptops, desktops, all of those. Then there are chips known as FPGAs and CPLDs. FPGAs, field programmable gate arrays, or CPLDs is computer programmable logic. It's been a while since I did this. Anyway, so FPGAs and CPLDs are simply millions of gates inside a microchip. You connect it to a hardware circuit. You design the chip on a computer, and then that computer program is sent to that chip, where each individual gate would be combined using these kind of laws. Okay, so FPGAs and CPLDs. Just going off a little bit tangent on how it's implemented. The reason we have these kind of laws is because you can actually design your own circuit. You can just buy an off-the-shelf chip, FPGA, which has millions of these gates. You write your own program, and you send that program to this chip, and the chip will do what you want it to do. Okay, it's called hardware description languages, HDL. All right, so AB is A naught plus B naught naught. So if you have a AND gate, you have an AND gate with two inputs, A and B, and the output is C, this can be implemented. And this seems counterintuitive because it seems as if you have a lot more gates that are required to do this. So you would have A, the output would be A naught. Then you have B, output would be B naught. And this A naught and B naught are given to a OR gate. So the output of this OR gate is A naught plus B naught. And the output of that is again given to a NOT gate. And so you get A naught plus B naught. Does this make sense? Not the reason why it seems like we are using 4 gates versus 1, but does the operation make sense? Implementation. Okay, that's how it would be implemented. It seems counterintuitive, as I said. You have one single gate that can do the function. Why use 4 different gates? Okay. So again, the reason we use different gates is because oftentimes we have these parts that are comprised of one single gate, millions of the same type of gate on one single microchip. You can buy it as an off-the-shelf component. You can write your own computer program, and you can program it to do what you want it to do. And as I said, the most fundamental building block is a NAND gate, N-A-N-D, NAND gate. So you would use these kind of equations to actually implement your functions. Okay. One point I'd like to make is that this is a 2-bit operation, and this is a 3-bit operation. 2-bit versus 3-bit operation. Okay. So that's where those De Morgan laws are used. All right. Let's see. 2 more gates, XOR and XNOR. Exclusive OR and exclusive NOR. This is not Twitter. This came a long time before that. Stands for exclusive. Exclusive. So that exclusion or exclusive is marked with a circle. Okay, it's marked with that circle. It's a OR gate, so it's A plus B, but because it's exclusive OR, that plus is circled. It's enclosed in a circle. So the XOR gate, the truth table for the XOR gate is this. You have A, you have B, and the output C is A exclusive B, exclusive summation. All right, so 4 combination again, 0, 0, 0, 1, 1, 0, and 1, 1. Exclusive OR, simply stated, the output will always remain low if the inputs are the same. Okay, the outputs remain low if the inputs are the same, which is here and here. Okay. Outputs are low when all inputs are the same. Okay. When the inputs are not the same, outputs go high. And the exclusive NOR gate is the exact opposite, right? The outputs will go low when the inputs are not the same. So XNOR, we have A, we have B. This is going to be easier to implement. A equals B naught. And this is 1, 0, 0, 1. Output is 0 or output is high when inputs are the same. And these kind of logic circuits are very useful when we want to implement, let's say, temperature sensing, right? If you have different sensors coming from different parts of your home, if all of them go low or all of them go high, logic 0 or logic high, then let's say it's time to turn on the AC or it's time to turn on the heat. So you have sensors in different parts of the home, right? Especially the distributed sensors now we see with the smart home monitoring systems. You put a temperature sensor in every every room of your residence. If the readings from any one of those are either 0 or 1, if all of them are the same, then the system turns on or turns off. You can design it. You can design the output of the system to do what you want. But that's the logic behind these kind of gates. When all inputs are the same, the circuit functions in a certain way, either 0 or 1, XOR or XNOR. And when any single input is different, then it's either on or it's off. Okay, so depending on our use case scenario, we can use either gates. All right, questions? Any questions at all? There are two more things I'd like to cover, two more slides, and then we'll end today's class. So remember I said we use NAND gates as building blocks. This is where I show you what we do. So NAND and NOR can both be used as building blocks. NAND gates are the easiest to implement. It seems, again, it says, as I said, it seems counterintuitive because NAND seems like a combination of two different gates. But in real life, when you build a circuit, it's the easiest circuit to implement. So you can use NAND gate to create all other gates. You take the input of the two NAND gates, short them together, and you get an inverter, NOT gate. And you can see from the truth table, A times A, I mean A and A NOT gives you A NOT. In circuit terms, if both inputs, you're only giving one input, right? If both inputs are high, meaning both are 5 volts, the output is 0 volts. If both inputs are 0 volts, the output is 5 volts. Implementation of OR gate, right? A plus B. That's where the De Morgan's laws are helpful. A is converted to A naught, B is converted to B naught. You give the output to a NAND gate again, you get A plus B. Excuse me. And then, of course, the AND gate would simply be taking a NAND gate and inverting or flipping the output. So you can implement all three gates using the same type of circuit. Same type of circuit. The same thing with the NOR. If you have a NOR building block, show the two inputs, the output will be an inverter. And the OR and AND operations will be exactly the opposite of the NAND gate. As straightforward as that. You take the NOR gate, invert the output, you get A plus B. You take two NOR gates, short it together, invert the outputs. So you get A naught and B naught. And then again, this would be A naught plus B naught, naught. And when you solve that, it becomes A naught naught times B naught naught. But that is a discussion for next week. All right, questions? Any questions? Any questions at all? There's a lot of information. As I said, in terms of time, we are only 67% done. But in terms of material, we are like 80% done. Probably more than 80%, come to think of it. We are at page 25. We still have about 15, 16 pages to go. All right, well, let's end class here today. We'll end class here early today. There's a lot of information, a lot of new information. So again, I always advise students, yes, we learn circuit analysis. Yes, everything is implemented in terms of circuits and components that we learn. But again, going forward, I mentioned this earlier, even before we begin op amps, right? You're taking off-the-shelf blocks, you're taking off-the-shelf parts and using them as building blocks. And this is especially true for non-EE majors, right? You're not going to be in there designing actual electric circuits, but you'll be taking off-the-shelf parts and designing a system. Or if you already have a system, you might be troubleshooting that system. And so you have to think from that aspect. It's great if students want to think in terms of voltages and currents, but that would kind of defeat the purpose of understanding digital logic. Okay, so keep that in mind. All right, so we'll end class here today. Bid you a good week, good weekend, and I will see you all on Monday. There may be a quiz, but I'm hesitant to keep a quiz over the weekend now. Okay, so it might be a quiz on Monday during class. Okay, a proctored quiz during class. So I'll think about it by tonight, and then I will post an announcement if I'm going to have a quiz on Monday. All right. Okay.